Good morning. Today's lesson we're talking about improper integrals. So we're going to split this into two lessons. Today we're going to talk about how we evaluate an improper integral that has infinite limits of integration. And then next lesson we're going to talk about how to evaluate an improper integral that has an infinite discontinuity within the interval of integration. So if you hear my dogs in the background, I apologize. They're kind of hyper today. So here is the definition of improper integrals with infinite integration limits. So really you need to know the first two and then the trick for the third one. So the first one, basically if you have a lower limit an upper limit of infinity, what we do then is we replace that with a variable, and then we take the limit as that variable goes to infinity. Okay, so then you would evaluate your integral. You would then plug in a and b and then take the limit as b goes to infinity. And same thing for when our lower limit is negative infinity, we're going to take the limit as a goes to negative infinity. Then the trick is if they're both infinity, negative infinity to infinity, then what you're going to do is you're going to pick a constant between the two. It doesn't matter what that constant is. Most of the time you're going to end up picking 0. And then you're going to split it up into two integrals using negative infinity to your constant and then your constant to infinity. And then you'll use rules 1 and 2 on each of those integrals. So in the first two cases, the improper integral converges when that limit exists. Okay? If the limit does not exist, then we say our integral diverges. And we're going to do an example of this in the first example so you can see what we mean. And then in the third case, we say the whole integral diverges when either of the integrals diverge. Okay? And what does it mean to diverge? It means that your area of, when you integrate, that interval of integration gives you actually an infinite area under the curve, and that's what it means to diverge. So let's take a look at that. So the first example had a typo in it, so my little handwritten infinity hopefully appears on your notes. So we are taking the integral from 1 to infinity of 1 over x dx. So the first thing we're going to do is we're going to go through and we're going to replace that infinity with b and take the limit as b goes to infinity. And then I'm going to go ahead and take the antiderivative of 1 over x, which is natural log. So now I have the limit as b goes to infinity of natural log of x from 1 to b. And both 1 and b are positive, so we don't have to worry about absolute value. So then from here, I'm going to go ahead and plug in my bounds. So make sure you keep the limit notation in front of your work the entire time. So I'm taking the limit as the natural log of b goes to infinity minus natural log of 1, which is 0. And then I can go ahead and evaluate this. And my natural log function, remember, has the y-axis, but it continually increases. So as b goes to infinity, my natural log also goes to infinity. So I get infinity here, and so I would say this diverges. And so if I wanted to look at the graph of 1 over x, let me put that back actually. Okay, so there's my natural log. Okay, but if I look at the graph of 1 over x, it's, something like this. Okay, so 1 over x. And then I'm taking the bounds starting at 1, and then I'm going to infinity. So I'm taking all of this area. And so what it means to diverge is it means that this area is never actually going to converge to a specific number. That area is always continually getting larger and larger and larger. And no matter what number you pick, however large, you can go far enough down on the x-axis that you will make sure your area is larger than whatever value you select. Okay, so infinite area there. All right, let's take a look at some other examples. So here we're going to do two examples that converge. So the first one is from 0 to infinity of e to the negative x dx, and then the second one is 0 to infinity of 1 over x squared plus 1 dx. So let's take a look at a first. So if I have 0 to infinity e to the negative x dx, the first thing I'm going to do is go ahead and replace that infinity with a b and take the limit as b goes to infinity. Then I can go ahead and take the antiderivative of that, which is negative e to the negative x. So I still have my limit as b goes to infinity, negative e to the negative x, and I'm evaluating that from 0 to b. Go ahead and plug in my bounds. So I still have the limit because b is still there. Negative e to the negative b minus e to the 0, which is just 1. So minus a negative 1, so plus 1. And then when I plug in my bound of infinity there in that exponent, we see that this right here goes to 0. So now I have just 1 is going to be my answer. So we can say this interval converges to 1. My next example would be from 0 to infinity of 1 over x squared plus 1 dx. And so here we're going to go ahead and change that to a limit. So limit as b goes to infinity of 0 to b of 1 over x squared plus 1 dx. Hopefully you're starting to recognize that when you have a sum of squares or things like that, that should start triggering. Maybe there's something about trig in this. So check your formula sheet. You should see that this is the antiderivative of arctan. So now I have the limit as b goes to infinity of arctan of x, evaluated from 0 to b. And then I'm going to go ahead and plug in my bounds. So the arctan, so I have the limit as b goes to infinity of arctan of b minus arctan of 0, which is 0. And so then the arctan of infinity, so tangent, arctan and tangent. Okay, so let's see here. Arctan, if you want to graph it real quick on your calculator, you can see it, or you can think about the tangent graph if you want, but it has horizontal asymptotes of pi over 2 and negative pi over 2. So my answer here would just be pi over 2 as we look as b is going to infinity. Okay, great. Next example, we have to use L'Hopital's rule. So let's look at how that might be a helpful tool for us. So we have 1 to infinity of 1 minus x times e to the negative x dx. So for this one, I see a product of two functions, 1 minus x and e to the negative x. So, I mean, I could try and distribute and use some u substitution, but that's not going to be helpful for that second integral because I'll have a negative x, and so if I just use u, it won't really replace anything. So I'm going to do integration by parts for this one. So I'm going to let u equal 1 minus x, so du equals negative 1, and then dv is going to equal e to the negative x dx, so then v is going to equal negative e to the negative x. So then, I put that backwards. I always like to organize it like this. You can organize these however you want. Okay, so then I'm going to go through and do my integration by parts. So then I'm going to have v times u, so negative e to the negative x times 1 minus x minus the integral of dv, so dx, so e to the negative x dx. Great. Okay, and so now we can go through and I'm going to distribute that negative e to the negative x, so negative e to the negative x plus x e to the negative x. And then I'm going to go ahead and take the antiderivative of e to the negative x, which is negative e to the negative x, but there's already negative, so positive e to the negative x plus c. And then combine like terms, so the first and third term will cancel, so I just get x e to the negative x plus c. All right, so this is, oops, I forgot. This is the integral without the bounds. So I have not taken into consideration the bounds yet. So then if I do take into consideration the bounds, so I know from 1 to infinity of 1 minus x e to the negative x dx is going to be the same thing as the limit as b approaches infinity of 1 to b, 1 minus x times e to the negative x dx. And so then I already know the antiderivative of that, so that's going to be the same thing as the limit as b approaches infinity of x e to the negative x. I don't need the plus c now because I have bounds from 1 to b. And then I can go ahead and evaluate this. So then I can plug in, so limit as b approaches infinity of, let's see here, b over, and then I'm going to move that e to the negative b to the denominator, so e to the b. And the reason why I did that was so that I could see that L'Hopital's rule will be helpful here. And then I have the limit as b approaches infinity of 1 over e after I plug in the 1. So the second term here is just 1 over e because it has no b's. But the first term, if I look at this, if I have the limit as b approaches infinity of b over e to the b, that's going to be infinity over infinity, right? Which then means L'Hopital's rule. So L'Hopital's rule, remember, is where you take the derivative of the numerator and the derivative of the denominator and then take the limit of those. So the derivative of b with respect to b is 1, and my denominator is e to the b minus 1 over e for that second term. So then now I can see that when I have b going to infinity, that first term is going to be 0. So my answer here would just be negative 1 over e. So that is going to be the value of that integral, which means if I look at this area, this graph is kind of funky. So the graph starts at 1 here, comes down, swoops, and then gets really, really close. And so if I'm looking at this, it's getting close enough here to the x-axis that this area is approaching a value, negative 1 over e. So even though it's adding infinite area, it seems like it's adding infinite area, that infinite area is converging to a specific factor. It's getting really, really, really small, that it's so small it's insignificant, and my area is approaching negative 1 over e. All right, last example. Infinite upper and lower limits of integration. So for this one, the first thing we're going to do is we're going to go ahead and split that up from negative infinity to 0. Plus 0 to infinity. And then if I look at this, I can think about e to the 2x as e to the x squared. So then I have 1 plus something squared. And so then if I use my u substitution, I could let u equal e to the x. And then by doing that, you see that essentially you just have arctan here is going to be what you have the antiderivative of, and your u is going to be e to the x. So, and that'll cancel with the other e to the x. If you want to go through and do the u substitution, you're welcome to. I'm going to skip that step for time. So then I'm going to get that I have, we got to change our limits. So I'm going to say the limit as a approaches negative infinity of a to 0, e to the x over 1 plus e to the 2x dx, plus the limit as b approaches infinity, 0 to b, of e to the x over 1 plus e to the 2x. And then we have our good old friend arctan. So then I have the limit as a approaches negative infinity of arctan of e to the x. Let me change my notation here. And that's evaluated from a to 0 plus the limit as b approaches infinity of arctan e to the x from 0 to b. And so then I can go ahead and plug that in. Arctan of 0 is pi over 4. So then I get that I have the limit as a approaches negative infinity of pi over 4 minus arctan of e to the a plus the limit as b approaches infinity of arctan of e to the b minus pi over 4. And then go ahead and look at that. So arctan, remember, our good old friend arctan, looks like this with our asymptotes at pi over 2 and negative pi over 2. So then I'm going to get pi over 4 minus, oh wait, never mind, because I'm not taking arctan of infinity. I am taking arctan of e to the infinity. So that is going to go towards 0. So then I'm going to get 0 here. Plus, right, so this goes to 0, is what I was talking about. This piece goes to 0 as a goes to negative infinity. And this piece goes to infinity as b goes to infinity. So that second term there, or that third term there, that will be my pi over 2. And then minus that pi over 4. So then I can go ahead and get pi over 2 after I simplify. So exciting, isn't it? Yay. Okay, that is your lesson for today. Go ahead, try your homework. Sorry, this video was